In this video, I'm going to discuss about moments of inertia of areas. The strength and rigidity of a beam is determined by the moment of inertia of its cross-sectional area. The computation of area moments of inertia is the main topic of this chapter. First, moments of areas, as discussed in centroids and centers of gravity, dealt with the integrals xdA and ydA. And discussing this topic are the second moments of plane areas, also known as moments of inertia. Integral of x squared dA and integral of y squared dA. Okay. Let's talk about the second moment or the moment of inertia of an area. So in the topic of centroids and centers of gravity, the first moments of the area of a plane region A, such as this one, plane region A, about the x and y axis were defined as this one. Moment of area about the x-axis. First moment of area, y times dA, integral of y dA. Okay. And also, first moment of area about the y-axis, integral of x dA, where A is the area of the region and x and y are the coordinates of the differential area element dA, as shown in the figure below. In the figure, sorry. The moments of inertia of the area about the x and y axis respectively are defined by this one, I sub x, or moment of inertia about the x-axis, is equal to integral of y squared dA, and moment of inertia with respect to y is equal to the integral of x squared dA. Because the distances x and y are squared, moment of inertia with respect to x and with respect to y are sometimes called the second moments of the area, y squared, y squared, and x squared. We now define the polar moment of inertia of the area A with respect to point O as the integral, like this one, moment of inertia of this area with respect to point O. Origin, or we call it pole, okay, polar, pole. Okay. This is the polar moment of inertia denoted by capital J. Is integral of rho squared dA, where rho is the distance from the pole to the element dA. Okay. An important relation may be established between the polar moment of inertia JO of a given area and the rectangular moments of inertia Ix and Iy of the same area. Okay. Noting that from Pythagorean theorem, rho squared is equal to x squared plus y squared. So we write J sub O equal to integral of rho squared dA. Replace rho squared by this one. And then distribute. Okay. Now note that the integral of x squared dA is I sub y, or moment of inertia with respect to y. And the integral of y squared dA is moment of inertia with respect to x. Therefore, the polar moment of inertia is the sum of Ix and Iy. So if you know the expression of Ix and Iy, you just add that is the expression of the polar moment of inertia. Okay, now certain cross-sections have, or various structural shapes have these properties, moment of inertia. Like this one. For a rectangle, these are the expressions of Ix, Iy, centroidal moment of inertia, and also the polar moment of inertia, or centroidal moment of inertia. Now, moment of inertia of a cross-section with respect to x and y, coordinate x and y axis, are derived using the expression, this one. For Ix, it's integral of y squared dA, and for Iy, integral of x squared dA. So these expressions, Ix and Iy, were derived using integration. Okay. Now for this one, centroidal with bars at the top, I bar, with respect to the centroidal x-axis and y-axis, x prime and y prime. Derived niya using another method called the parallel axis theorem. So later, we will derive this one, these expressions. For a triangle, such as this, x lang, x kaya ang side is, one side is along the x-axis or sometimes parallel. Okay. But for a right triangle, we can have an expression of Iy for a right triangle. This expression is with respect sa x-axis, and this one is with respect sa centroid. And we also have for circle, this one. And notice that since J sub O is equal to Ix plus Iy and equal man, so 1/4 pi r raised to 4 times 2 lang, ka-equal man ng Ix, times 2, the result is 1/2 pi r raised to 4. And we also have for semicircle. Now, we still don't have an expression of moment of inertia with respect sa centroid. We still have to derive it using parallel axis theorem. Okay. Now, this is the parallel axis theorem. There is a simple relationship between the moments of inertia about two parallel axes, provided that one of the axes passes through the centroid of the area. Okay, you have to remember this. In order to use parallel axis theorem, one axis must pass through the centroid of the area. Okay. Let's consider the moment of inertia Ix. Ix lang of an area A with respect to an arbitrary x-axis. Any axis except sa kining centroid. So pwede diri x, pwede dira x. Arbitrary x-axis. It could also be the coordinate x-axis. Denoting by y the distance from an element of area dA, the distance of dA to that axis, to the arbitrary axis, denoted by the distance y. Okay? Now, we recall that I sub x is equal to integral of y squared dA. Diba? Now, let us now draw. Remember, moment of inertia with respect to x, integral of y squared dA. So, the distance y is the distance of the element dA to the x-axis. Now, Let us now draw the centroidal x prime axis, this one. So the centroidal x-axis is the axis parallel to the x-axis, which passes through the centroid C of the area. Denoting by y prime the distance from the element dA to the centroidal axis, denoted by the distance y prime, we write y is equal to y prime plus d, where d is the distance between the two axes. D. Substituting for y in the integral representing ix, you replace y by this one, y prime plus d. We write this one. And if we expand na to, now, let's recall. Moment of inertia with respect to x is equal to integral of y squared dA. Again, y is the distance of dA from the arbitrary x-axis. Now, for this one, integral of y prime squared dA, this is also I. This is also a moment of inertia. The reference is the centroidal x-axis. Again, pag ix, y squared, distance of dA from the x-axis y. But if the distance is y prime, then the moment of inertia is with respect to x prime. Okay. Okay. So again, the first term is the moment of inertia with respect to the centroidal x-axis. The second term is, this is first moment of area. But then the reference is centroidal x-axis man. Therefore, if you sum up, the total is equal to 0. Like if you want to imagine a rectangle, every element above the neutral axis has a corresponding element below the neutral axis. So if you get the first moment of the two elements, it will just sum up to 0. Same area, same distance, pero negative ang below the neutral axis. So ang sum sa duha, 0. Okay. That is why the integral of y prime dA is equal to 0. Kaya ang reference ani, centroidal x-axis man. For the third term, the integral of dA is simply the total area. So therefore, if this is 0, and this is ix prime, and this is a, the final expression of I sub x is this one. This is the parallel axis theorem. And again, sa previous slide, it was mentioned na in order to use parallel axis theorem, one of the axes must pass through the centroid, which is this one. Kinina x is any axis. Arbitrary ni siya na axis. While this one is centroid. So whether you are considering a single element or the whole area, the first term sa right side is always centroidal na moment of inertia. So this formula expresses that the moment of inertia Ix of an area with respect to an arbitrary x-axis is equal to the moment of inertia Ix of the area with respect to the centroidal x prime axis parallel to the x-axis plus the product AD squared of the total of the area A and of the square of the distance D between the two axes. So, ang kining D ay distance between the centroidal axis and the arbitrary axis. This result is known as the parallel axis theorem. So, a while ago, when I showed the properties of different cross-sections, we saw the rectangle ba? The moments, the expressions of I sa rectangle. No? Let us try to derive the expression of the centroidal moment of inertia using this parallel axis theorem. Okay. Now consider this rectangle. First, let us solve the moment of inertia with respect to x and y. And coordinate axis x and y. I have said na those expressions were derived using integration. Okay. So if we use integration, of course, we will analyze a rectangular strip. So if we start with Ix, then our strip must be horizontal. Okay, the distance of this strip from the x-axis is y, and ang thickness niya is dy. Now, this is the expression of Ix, integral of y squared dA, and our dA is this one, differential area, and it is equal to b times dy. And dy man ta, ang limit sa y is from 0 to h. B is constant, so if you integrate, you have this one. And you substitute. Okay. This is the moment of inertia with respect sa x-axis, or sometimes we denote this one as moment of inertia of the base of the rectangle, 1/3 bh cubed. Now, for IY, the rectangular strip must be parallel sa y-axis. And the distance of this strip from the y-axis is x, and the thickness is dx. And again, this is the expression of IY, integral of x squared dA. Our dA is h dx. And dx man ta, ang limit niya is from 0 to b. And then substitute. Okay. Same lang o coefficients, ang exponent lang. For Ix is h cubed, for Iy. Sorry, this is Iy. Iy. B cubed. B cubed h. Now, for centroidal moment of inertia, okay, suppose this is the centroid, no? And this will be our centroidal axis x prime and y prime. Okay. This distance is 1/2 sa b, x bar, and also y bar, h/2. This is the parallel axis theorem. Kining Ix, mao na ni siya. 1/3 bh cubed. Okay. Mo ni ato unknown, centroidal moment of inertia. Area is simply bh d. Again, d is the distance between the centroidal axis and the arbitrary axis. In this case, our d is this one, y bar, h/2. So, kung ato yung substitute, this is the result. 1/3 bh cubed, I bar, area, d squared. And then simplify, and then transpose. Mao niya ang result, 1/3 minus 1/4. Okay. Do the same for y. This Iy is this one, 1/3 b cubed h. Ang d na sad, distance sa centroidal y-axis and the arbitrary y-axis. Distance ano, centroidal y-axis and arbitrary y-axis. And that is b over 2. Okay. And then simplify, and then transpose. Okay. Same lang coefficient 1 over 12. And the exponent is b cubed na instead of h cubed. So kung ato i-check ni tanan with respect sa base and with respect sa centroid, man, di ba? Centroid niya base. Okay. So for triangle, this one, kung yun sa pag-derive ni, same lang. Ix equals centroidal plus area of triangle. This is our D. Distance between centroidal axis and the arbitrary. And the result is this one. Okay. So we can now solve some problems now para ma-apply na to ang parallel axis theorem, especially for composite figures. Okay, first problem. Determine the moment of inertia Ix of the area shown with respect to the centroidal axis. Now, a while ago, with respect to sa x, and ang centroidal ato is for a single structural shape or a single cross-section. Now, pag built up or composite figure, first is we determine or locate the centroid, y bar, and we will use Varignon's theorem. Okay. So we will subdivide this one into two elements. No? So let's locate the centroid. Ginani pag subdivide 60. So 60 is okay, by 40, and the other one is 80 by 20. Okay. So area 1, it's 80 by 20, and that's 1/6. Area 2 is 40 by 60. That's 2/4. So the total area is 4,000. Why? Why 1? This is element 1, no? Ang yung centroid na there. Okay. The distance of this centroid, this point from the x-axis is this. And that is equal to 60 plus 10, 1/2 of 20. That's 70. So this is 70. And for the second element, 60 man eh, nadiri ang centroid sa middle, and y2 is 30. And for this column, you multiply y and a, 70 times 1,600, 30 times 24, and then we add. And we can now solve for y bar. It's 46 millimeters. Okay? So now we can now compute for the moment of inertia. Okay. What we'll do is this one. The centroid of the whole area will now be our arbitrary axis. This one, centroidal axis of element 1, x double prime, centroidal axis of element 2. This one is our arbitrary axis, which is the centroidal axis of the whole area. This one, centroidal axis of element 1. This one, centroidal axis of element 2. Our arbitrary axis is the centroidal axis of the whole area. Okay. So let's first consider element 1. So for element 1, the centroidal moment of inertia is this one. 1 over 12 BH cubed. 1 over 12 ET times 20 cubed. Okay. This one. Centroidal na eh. So we can now compute for the moment of inertia of element 1 with respect sa x-axis, centroidal na x-axis. We use parallel axis theorem. So we transfer the moment of inertia of 1 from its centroidal axis x prime to the parallel axis x. So this one is getting 53.3 times 10 raised to the power of 3. Area 1, of course, that's 1/6 ET times 20. Ang D1 is distance sa duha ka axis, distance between x prime and x, x prime and x. Pila man eh, distance. Okay. First, compute sa nato na eh. 60 man eh, ha? Kayang middle man siya. 30. So 30 siya din. So 60 tanan. 60 minus 46. This is 14. Okay. And this is our D1. Distance between x prime and x. X prime and x. And this is equal to 24. 14 plus 10. So we can now substitute this one sa parallel axis theorem. Okay. And this is for element 1. Next is element 2 and then i-add yun. For element 2, first we compute for the centroidal 1 over 12 BH cubed. 1 over 12 B40 height 60 cubed. And then we compute for D2. D2 is the distance between the centroidal x-axis, x double prime, and the x-axis. 46 minus 30, D2 is 16. This one, centroidal 720 times 10 to the power of 3 plus area 224, 40 times 60, D2 din. This one. And i-add yun, i-add ang sa element 1, element 2. The total moment of inertia with respect to the centroidal axis sa composite figure is this one. 2.31 exponent 6. Okay. Now, I have my own style of solving for the centroidal axis, or centroidal moment of inertia rather. Okay. My style is this. I will try to get rid of D1 and D2 para to avoid confusion. Okay, this one. First is I will use parallel axis theorem. So I'm going to transfer the moment of inertia of element 1 and 2 from its centroidal, this one, centroidal axis. This is x prime. Forget about this one, x prime. Okay, different one. Focus on this figure. I-transfer na ko ang moment of inertia of element 1 and element 2 from the centroidal axis to this one, this arbitrary axis, coordinate axis na x. Okay, then ako i-transfer. Mao man ang expression. X prime, sorry X prime and X double prime man eh. Basta centroidal. And this one is this one, x-axis. This is the distance from the centroidal axis of the individual area, meaning distance sa centroidal axis to our arbitrary x, 70. For element 2, 30. Di ba? It's very easy. Distance of the centroidal axis of each element to our arbitrary x-axis. So our D1 is 70, our D2 is 30. Yeah. Okay. This is the result. 1/12 base 80, height 20 cube, area 16, D na yun, 70 squared. For element 2, centroidal plus area D square. Mamaya ito D2. The result is this with respect to x. Now, this is for the whole area. Sum of 1 and 2, whole area. Next is, I will no longer consider this one, but I will consider the whole area. This is the centroid of the whole area. And this is the centroidal x-axis, denoted by x prime. And I will use parallel axis theorem. Given this one, solve for ix prime. So again, using parallel axis theorem, we transfer the moment of inertia of the area from axis x, this one, passing through the origin, to the parallel axis x, x prime, passing through the centroid. Now, for this formula, ang ix man ang known. Kini ang unknown, ix prime, di ba? So, I sub x given unknown area, since whole area then 4,000. 16 plus 24. And d yun is distance between x prime and x. Distance between x prime and x. Centroid man eh. 46 squared. The result is this. Okay? Same naman sa previous na solution. Exponential yan to. Scientific notation ba? 2.31 times 10 to the power of 6. Same lang. Ang advantage is dili na ka magkuha og D1, D2, and so on. You are just using the centroidal distances of every element. Since pagkuha sa centroid, mora ang imong gigamit na values. Wala na ka nag-solve og D1, D2, D3. Let us solve another problem. Compute Ix and Iy for the region shown with respect to the centroidal axis. Now, since composite na siya, first is i-subdivide mo into different elements. Okay, so one way of breaking this figure down into several elements is i-cut nimo dire. Cut siya kadiya. Therefore, we have 3 elements, 1, 2, and 3. So, therefore, this area is equal to this one. Element 1, which is 80 by 20, plus this one, element 2, 25 by 90. Okay, 25 by 90. Plus this one, 60 by 30. We have 3 elements, 1, 2, and 3. So first is ilocate ang centroid. So construct a table. No? Okay, ilocate na to. Centroid sa element na dito. Okay. And it's 40 and y1 is 10 kay 20. For this one, nadali ang centroid. Okay, our x is 12.5 and ang atong y is 1/2 of 90. That's 45 plus 20. That's 65. And then for element 3, x of 3 is 30, 1/2 of 60. For y3, that's 1/2 of 30, that's 15, plus this one, 90, so 105 plus 20, this one. It's 125. After this, you construct a table and then supply values. Area 1, ET times 20. 16. Area 2, 25 times 90. That's 250. Area 3, 60 by 30. 1/8. So i-add mo, the total is 5,650. Okay, x1 is 40, y1 10, x2 12.5, y2 65, x3 30, and y3 125. And then multiply xa 40 times 16, and so on. Okay. After this, you sum up 64,000 plus 28,125 plus 54,000, this one, and also with YA. After this, we can now solve for the centroid. X bar, summation of XA over summation of A. Okay, lowest forms of fraction, decimal form is 25.86 millimeters. Y prime, this one, 68.54 millimeters. So after this, we can now compute for the moment of inertia. Okay. This element 1, 2, and 3. These are the areas 16, 250, and 18. 80 by 20, 25 by 90, 60 by 30. Centroid sa element 1, 2, and 3. Okay? So let us start with IX. Centroidal moment of inertia with respect sa x-axis. So sa x, we need y distances. Y distance. So y1 is 10, y2 is 65. Same value as sa previous na slide. And y sub 3 is 125. 90, 90. So 1/2 is 45. Plus 20, 65. This one, 30, 1/2 of 30, 15, plus 90, plus 20, 125. This is the centroid. Centroidal x-axis, x prime and y prime. And this is our y bar. Fraction na, it's 7,745 over 113. Again, so ano? Okay. So first, let us use the conventional na solution. Okay. I am changing the centroidal to I sub G because other subjects are using this notation for centroidal moment of inertia. Again, this is still centroidal moment of inertia, but I am using the notation I sub G. Moment of inertia with respect sa center of gravity or centroid. Okay. Sum up nito. Okay. For the first element, we solve for D1. Since all of the elements are rectangles, same lang ilang centroidal, 1 over 12 BH cubed. And then area given D na lang. Okay, so let us start with D1. Ang D1 is distance sa kinina axis x prime to the whole area na x prime. Kana. And that would be y bar minus 10. That's 6,615 over 113. So our first term, for first element, we have this one. 1 over 12 BH cubed plus area times D squared. Now for element number 2, this is our D sub 2. Distance between the centroidal x-axis of 2, element 2, and for the whole area na centroidal axis. Now this one is equal to y prime minus 65. This one. And it's 400 over 113. And yun na sada. Element to centroidal, area, and then D square. And for element 3, this is our D3. Distance between this centroidal axis and centroidal axis, a whole area. This one is equal to 125 minus y bar. Ano? So, i-add lang nimo ni. The result is this. 12,956,286.87 millimeters to the fourth power. Next is IY, okay? By the way, please do not get confused with this. This one is centroidal moment of inertia of the individual areas or individual elements, while this one, centroidal moment of inertia of the whole area. Okay? So for IY bar, this one is 40. Yeah? This is 80 man. So 1/2 is 40. Okay, this one is 12.5, 1/2 sa 25. And this one, that's 30, okay, 60 man. So 30. And this one is our X bar. 5845. Recall na to. Okay, muna to X bar. 5,845 over 226. Now for Y, the centroidal moment of inertia is 1 over 12 B cubed H. D na sada. Distance between the two axes. Y, So for D1, we have this one. Distance ani na Y o ang sa whole area na Y. And that is equal to 40 minus x bar. This one. 1 over 12 B cubed H. And for element 2, Dito na sa ta. Okay, this one. This is equal to x bar minus 12.5. This one. You can check this one. Okay. And then for element 3, money on D3. Ano? D3. And this is equal to 30 minus x bar. Money ang result. And then you add. Okay. It's 2,262,877.03. Okay. So, if you want to get rid of D1, D2, and D3, you can use my style. Okay. Okay, this one. So my style is first, compute the moment of inertia with respect to the coordinate x and y axis. So let's recall. Mamo ni atong tulo ka elements, no? I-transfer nato ang moment of inertia sa tulo ka elements from its centroidal axis to the coordinate x-axis. Okay. This one. For individual, and then kinsa for x-axis. Okay. Element 1, 1 over 12 b h cubed, area 16. 10 naman na, distance sa centroidal axis of element 1 to the x-axis, 10. For element 2, 1 over 12, 25, 90 cubed, kini sa DND, 65. Okay. So, manotice ninyo na wala tayo nagamit o wala tayo nag-solve og D1, D2, and D3. We just use y distances sa pagkuha sa centroid. And the result is this one. And you do the same for y. Yeah. So, ang distance, basta pag IY is, ang distance is horizontal. Distance between y-axis sa element o y-axis sa coordinate na y-axis. So 40 for this one is 12.5. For element 3 it's 30. Okay. But do not forget sa centroidal. Dapat b cube each, b cube each, b cube each. And the total is this one. Okay. Now, after solving for this one, coordinate axis, proceed ka sa whole area. Okay. Now, this is the centroid of the whole area. Our objective is to get the value of I with respect to x prime and y prime. Okay. So, using parallel axis theorem, kini sa itong unknown. This one, katong na-solve na to. Previous nga slide mo to siya. With respect sa the axis. And then centroidal. Now, our whole area is 5,650. Sum patolo. Let's substitute. This one, Ix, ganyan, with respect sa coordinate na x-axis. Ix ba centroidal, whole area, D is y bar squared. Okay, 12 million. Kung ito i-check, cross-check or double check, muna ang result, conventional na solution. Same lang, 12, 956,286.87. Same lang. For IY, okay. Use the values of previous slide, this one. 6 million. And ang D na to is ang X bar. Okay? Okay, Y man. Distance between the two Y axis. It's X bar. Mana ang result sad? Kung ito i-double check or i-recall na to ang previous na method, man. Previous na solution rather. Okay. So, in solving centroidal moment of inertia, you can use the conventional way of solving it or you can use my style. Okay. Na dili na mag-solve og D1, D2 and D1, D2, D3 and so on. Okay. First, i-transfer siya sa coordinate axis. Then after that, i-transfer na sa nimo sa centroidal na moment, centroidal na axis, so X and Y. So I hope that you have learned something from this video. Thank you for watching.